Hello guys, this video is in continuation of your earlier class. In the last class we were discussing about VV connection or open delta connection. Now let us move to the merits of VV connection. So we know that if one of the transformers in the delta-delta connection is inoperative, that is if it fails, then it is possible to enjoy the three-phase supply by open delta connection with a reduced capacity. And we also saw how much is the reduction, that is 57.7%, right? So in three phase load is small, whereas in VV connection it is economical. That is, if load is small, then we can have the VV connection since one transformer is not required, right? If three phase load is small, then we can go with this. So even if there is increase in the load in the future, just by adding one transformer to the existing VV connection, capacity also can be increased. Okay, that is the third merit. Fourth is the connection acts as a automatic standby. So that's what, even if you are trying to increase the load, then you can have one more transformer into the service by making open into close connection. So there it acts like an automatic standby, so you can use in the future also. So coming to the limitations, the first limitation you can see here is the power factor for which your VV bank is operating. Now let us see the limitations. At the first we have, so we know that the average power factor of open V connection or open delta connection will operate less than the load connected. Usually the power factor is around 86.6% of the balanced load power factor. Okay, here the power factor of VV connection is less. That is what you need to remember. Second one, two transformers in VV bank operate at different power factor except for balanced unity power factor load. Means even if you connect a balanced load, the two transformers which are connected in VV connection both operate at different power factors. It is not like the load is balanced and the power factor by both of the transformers is same. It is not like that. Power factors of both the transformers are different. So if the terminal voltage, that is on the secondary side of the VV connection, if it becomes unbalanced, so even this may happen even though load is perfectly balanced. What it means is, even though load is perfectly balanced, the terminal voltage may phase of getting unbalanced. This is the third disadvantage of VV connection. It is not like your delta-delta connection. Okay, here terminal voltage may face problem of becoming unbalanced even though load is perfectly balanced. So here the formulas are given here. The power factors, the power of the two transformers that is connected in open VV connection. First formula is P1 is equal to kVA cos 30 minus phi. P2 is equal to kVA cos 30 plus phi. One will operate at cos of 30 plus phi, whereas other one will operate at cos of 30 minus phi. Okay. So this is, you need to remember, this will help while solving the problems. Now let us move to the next topic, that is conversion from three phase to two phase connection. That is, we are going to connect the applied three phase into two phase by using Scott connection that was initially proposed by C.F. Scott. So what exactly it says is, you should be having two transformers, preferably of same rating. Even if you have different ratings of transformer, it is possible, but better to have two transformers of same rating, single phase transformer, and with available suitable tappings available on the transformer. So we have to connect those two transformers in such a manner that your teaser transformer is connected at 86.6% of the tapping, whereas your main transformer is connected with the teaser transformer at 50%. Okay, where the other two ends of the main transformer are given to Y and B, and the teaser transformer end is given to the R. Here there is no such neutral here, like there is only physical neutral here. Don't assume like this point O as a neutral. And here we read line to line voltage. Either you measure between R and Y, or Y and B, or between R and B. Okay. The number of turnings with respect to teaser transformer in primary and secondary will be same, as well as in the main transformer also the number of turns in the primary and secondary will be also same. And here you can see the small r, small y, small b are taken out from the teaser transformer as well as the main transformer, and y and b is with respect to at the junction of main transformer teaser transformer, that is B, and the y is the your main transformer itself. Okay, so this is what the Scott connection is. So we are taking help of this connection to convert the applied three phase into two phase. So such two phase is required for to give supply to the furnaces. Even if you want means you can take three phase out of two phases here just by connecting with R, Y and B. Okay, you can get even three phases even though it is converting into two phases, but the connection should be such a manner that as shown in the figure 2.9.1. Okay, hope this is clear. Teaser transformer is connected at 86.6%, whereas teaser transformer and main transformer is connected at 50% tapping of the main transformer. Okay, and the remaining is as per the diagram. Like I told you, it is used for to supply the furnace, and all with having phase difference of 90 degree. Here the same connection whatever we just now saw is the same here also, but with slight changes. It is exclusively for what connected. We are going to connect here two loads here, one with respect to the teaser transformer, one with respect to the main transformer. Okay, you can see this is the secondary side of the teaser transformer, and this is the secondary side of the main transformer. Okay, actually it should be M here. Okay, I to N, it is I to M exactly. Okay, and again whatever the number of turns in the secondary is with respect to same with the primary when it is compared with the main transformer or it is teaser transformer, number of turns are same. So that's why you can see that the voltage across the teaser transformer in the secondary V2T it is, and voltage across the main transformer secondary is V2M. You can see both the voltages are what? They are having a phase difference of 90 degree, whereas your I2M and I2T will fall on the same with respective voltage phasors, even though your current is also having the phase difference of 90 degree. Okay, this is what the requirement. If the requirement is like this means we have to go for the Scott connection. If the phase difference is required 90 degree and the voltage should be same, then you have to go for the Scott connection. Okay, so let us come to the calculation. Like I told you, the point O is not neutral point of the three phase supply. Should not misunderstand that this is the neutral point. This is not the neutral. Neutral will be somewhere here. You can call it as virtual neutral. Okay, it's not like something going to get tapping over there. It is somewhat like a virtual neutral. That's why showing the dotted line. Okay, so we know that from this point to this point. Okay, from R to as well as your O. So whatever the voltage applied is what? Root 3 by 2 times that of N1. Yes or not? That is 86.61% of that of N1. Say whatever, see if N1 is 100% means I am using only 86.61% of that. Okay, so that is nothing but root 3 by 2 times of N1. Okay, so now next we know that this is the phase voltage. I mean this is the line voltage. Yes or not? VL. It will be anyhow it is measured between R and Y, or it is measured between Y and B. If I want to know what is the phase voltage means, how I am going to measure? I require one line as well as neutral. Okay, I require one line as well as neutral, or one phase or neutral. So we know that formula with respect to line voltage is what? Vp is equal to VL by root 3. Yes or not? VL by root 3, because if you are going to measure the voltage between phase voltage, means it will be measured between phase and as well as neutral. So let us assume somewhere neutral comes here. We don't know exactly where it is and all, but neutral will come here if you want to find the virtual neutral. So it is what? 1 by root 3. Yes or not? 1 by root 3 times of N1. So that's why what we are going to do here is by root 3 times of VL. Okay, any of N1 you can take it as like this. Any of VL and N1 are proportional. So we know that root 3 by 2 N1 is greater than that of 1 by root 2. Sorry, 1 by root 3 times of N1. Yes or not? Because it's 86.6% and 1 by root 3 is 0.577. Yes or not? It is 57.7%. True. So I need to what? Subtract root 3 by 2 minus 1 by root 3 so as to get the exact neutral point. So after subtracting, what I get here is 0.288 times of VL. So neutral is somewhat 0.288 times of VL, somewhere here. So this 0.288 is nothing but, what? It is 1/3 of 3. Yes or not? It is 1/3 of 3. Because if you multiply 0.288 into 3 times, means again you will be getting what? 86.64, 86.4 somewhat. Okay, almost approximately equal to 0.86. Or if you multiply 0.289 into 3, it is exactly 86.7. So exactly if you multiply 0.28 into 3, means what happens? You will get what? 86.67. Again getting back the whole number of turns. So what I understood here is your ratio, that is whatever your n is dividing, right? The Teaser transformer at RO and all. So RO, it is in the ratio of what? 2:1. It is in the form of 2:1, because 0.289 into 3 means it is 86.67 full whole percent. So now I got is the length of you can say NO. The length of NO is how much? Length of NO is 0.289, and again this is in terms of what? It is 2:1 ratio. It is in that form of 2:1 ratio. So that's why I can see N divides the Teaser winding RO in the ratio of 2:1. That's why it is given 2:1. RO in the form of 2:1. So this will be 1 and this will be 2 times. This is 2 and this is 1. Okay, hope you understood this. That is Rn is 2 and NO is 1. So it is 2:1 ratio. Okay. Now coming back to the calculation, we know the transformation ratio K is equal to I1T by I2T is nothing but is equal to N2 by N1. This is already you know. Anyhow, we are writing the transformation ratio for Teaser transformer. It will be what? Primary current by secondary current of Teaser transformer. So consider that particular part. So I1T is equal to I2T into N2 by N1. Since we know that N1 we are not using complete, N2 we are using full, but N1 is how much? How much you are using N1? This is what N1, right? We are using how much? It is root 3 by 2 times of N1. That is 86.61% we are using. That much only we are using. Yes or not? That's why N1 is replaced by root 3 by 2 times of N1. Again, rearranging the things here. 2 goes up. Root 3 comes at the bottom. N2 by N1 into I2T. So 2 by root 3 if you do, means I will get what? I1T as 1.15 times of N2 by N1 into I2T. Or can replace N2 by N1 by K. So I1T is equal to 1.15 times of K times of I2T. So this is the formula which you need to remember. So here 2 things which you need to remember here is primary winding of the main transformer carries I1M consisting of 2 parts. Okay, main transformer. Where is main transformer? This is the main transformer. This is the Teaser transformer. So your main transformer consists of 2 parts, that is I1M. I1M coming from this side as well as I1M coming from this side. Okay, consists of, it handles 2 currents. The first half, the first balance is the main current I2M. Okay, here the first half is this much, that is N1 by 2. It will balance the main current, that second current, that is I2M. I told